Okay, this is chapter 7, which is all about energy. You've heard of the energy crisis, energy conservation. Well, energy is a physics concept. And here's some of the things we'll talk about in this chapter. So we start with work. Work in physics involves a force and a distance. And in particular, it's equal to force times distance. So our equation is W for work equals F times D. F is the force, D is the distance. So two things are always occurring. There's an application of a force on an object, and that thing has to move. So here's a guy, if he's pushing on a wall and the wall doesn't move, then in physics we would say he does zero work. But if he pushes with force F on some crate and it moves a distance D, then the force times the distance is equal to the work. And there's a unit there. Newtons of force times the distance in meters gives newtons times meters. Or you can call that joule. The unit has a special name in physics called a joule. 1 joule is 1 newton times meters. Some examples. Here's a load which is being lifted. If you lift twice as much weight, then it requires twice as much work. And that's because the force needed to lift twice the load the same distance is twice as much. So you do twice as much work. Also, if you have one load and instead of raising it 1 story, you raise it 2 stories, that also requires twice as much work. The reasoning here is that the distance is twice as great. Either way, you've doubled the work. Power is a measure of how fast the work is done. The equation for that is simply work done divided by the time interval. The unit of power is a joule per second, named after James Watt, the developer of the steam engine. It's called the watt. 1 joule per second equals 1 watt. You may have heard of kilowatts. A kilowatt is just 1,000 joules per second, or 1,000 watts. And here's a rocket, which does a lot of work in a very short amount of time, so it's a high-power rocket. So somebody running up the stairs is using more power than if they climb the stairs slowly. Now, if you have twice the power of an engine, it means it can do twice the work of one engine in the same amount of time. Or it could do the same amount of work of one engine in half the time. So here's a boat that has 600 horsepower, which can be converted to watts through 1 horsepower is 746 watts. This boat can speed up twice as fast as this boat, which only has 300 horsepower. So back to energy. Another form of energy is potential energy. Potential energy is stored energy that could do some work. So there's elastic potential energy, like a stretched bow has some stored energy in it, and it can do work on the arrow, causing it to speed up. A stretched rubber band in a slingshot also has elastic potential energy. There's also a form of potential energy called gravitational. This is potential energy due to the fact that something is high off the ground. And so an example is this coffee mug in the top shelf. It has the potential to fall and smash and make a big loud noise, so it has some gravitational potential energy. And there's even an equation for it. It's the mass of the object times g, the acceleration due to gravity, times the height that it is off the ground, mgh, where g is 9.8. Another form of energy is kinetic energy. This depends on the mass of an object and the square of the speed times a half. So the equation is actually 1/2 times mass times speed squared. So this means if you speed an object up, double its speed, you quadruple the amount of energy it has of its motion. So it turns out there's a work kinetic energy theorem, which is that the kinetic energy of an object is equal to the work that was done on it to speed it up. So an equation form, the net force on an object times the distance it goes is equal to 1/2 mv squared. So here's a car, it has some net force on it, F, goes the distance d. F times d is going to give you 1/2 mv squared as final kinetic energy. So there is a law of physics called the law of conservation of energy, which just states that in a closed system, an energy cannot be created or destroyed. It can only be transformed from one form to another. So an example of this diver starts off with potential energy 10,000 joules, but he's not moving. As he falls, that 10,000 joules of energy transforms into kinetic. So that by the time he has zero potential energy at the bottom, he has 10,000 joules of kinetic energy. So a machine is a device which multiplies forces or changes the direction of forces. And one of the principles of machines is that they cannot create energy, like a simple machine, but it can transform energy from one form to another, or from one location to another. But it cannot multiply work or energy somehow. Here's a pulley, here's an inclined plane, here's a lever. So the principles of a machine are based on the conservation of energy, which is that the work you input is going to be equal to the work that you output. Okay, that's if there's no losses. So if you look at work in terms of force times distance, the input force times the input distance equals the output force times the output distance. And here's an example of a big pulley system. This weak man is pulling with some small force, but he's pulling a whole lot of string some large distance. Meanwhile, this 500 newtons, very heavy mass, is going up some small distance, but it takes a very large force to raise it that small distance. And so these are equal. The simplest machine is a lever, which rotates on a point of support called the fulcrum, right there. And it allows a small force over a large distance d to be converted to a large force over a small distance. Again, obeying this rule, Fd input equals Fd output. A pulley, arranged like this, like a fixed pulley, can change the direction of the force, but not the magnitude of the force. You can also have a movable pulley, which can actually change the amount of force. So here you're lifting this load with half the force, but you're pulling it up a smaller distance. If you pull 1 meter up, the block will move half a meter up, but the output force will be doubled. Efficiency is the percentage or the fraction of the work that's put into a machine that is converted to useful work output. So the ratio here is the useful energy output divided by the total energy input. That's the efficiency. So here we have a locomotive. It's burning up some energy. Some of that energy is being created to waste heat. It comes out in the steam that goes in that you see. And some of it is converted into the kinetic energy, which is actually moving the train. So your efficiency would be this kinetic energy, the useful energy output, divided by how much you're burning. And this is waste. Now you can actually recycle your waste energy. And this was done by Thomas Edison when he first made some power plants in New York. He realized that these created a lot of heat, and he used this heat to heat nearby buildings. But typically these days, power plants are built far away from houses, and they just simply waste 30% of their energy into heat, either into the smoke about like the steam or into nearby rivers. So sources of energy, our main source of energy is the sun, and there's lots of ways we can get energy from the sun. One is this water cycle. Sunlight comes down on the earth, uses its energy to evaporate the water, which then falls as rain. Rain flows in rivers and into generator turbines, which gives us useful energy, and then that water returns to the ocean. Also, the sun doesn't heat every part of the earth equally, so it generates wind, which can turn turbines. You can also get sunlight to produce electricity directly through photovoltaic cells, like solar energy panels on rooftops, that can make electric energy directly. And it turns out that more energy from the sun hits the earth in 1 hour than all the energy consumed by humans in an entire year. So that's a good source of energy. Now a fuel cell uses hydrogen and oxygen to combine to make water and energy. And this is just the opposite process of when you run electricity through water. You can create bubbles of hydrogen and oxygen. If you reverse that process, you can create energy that way. There's also nuclear energy, which uses uranium or plutonium and again generates heat, usually turns a turbine. The advantage of nuclear energy is that it doesn't pollute our atmosphere, but the disadvantage is that it creates radioactive waste, which, if you store it near humans, can be toxic. Okay, Chapter 8 on rotation. So when an object turns about an internal axis, it's undergoing rotation, and all the particles in the object are actually going on circular paths where the centers of all the circular paths are along this same rotation axis. Okay, so rotation is characterized by two kinds of speeds: the tangential or linear speed of the particles in the object, and the rotational speed of the whole object, sometimes called angular speed. So it turns out that if you have one rotating object, the distance traveled by a point on that object is called the tangential speed, and that is greater for objects closer to the edge or the circumference, and it's smaller for points that are closer to the center. So, for example, you have this turntable with a record on it, or a CD, going around and around, and there's a little bug sitting on it that's halfway between the axis of rotation and the edge. He's going fast, but the bug right on the edge is going twice as fast as that guy. So we measure angular speed in radians per unit time, radians per second. And the symbol for angular speed is a W, which is sort of curved, and it's actually the Greek letter omega. But all parts of a merry-go-round have the same value of omega, so they all have the same rotational speed or angular speed. But the tangential speed of particles or people on it is greater the further the radial distance from the axis. So this guy has 0 tangential speed, this guy has more, and this guy on the edge has the greatest tangential speed. So the equation there is V, tangential speed, is equal to R times omega. So any object that's rotating tends to want to keep rotating unless acted upon by some external influence, and that's called rotational inertia. It has a symbol I, and it depends not just on the mass, but also the distribution of the mass around the axis of rotation. So for example, this dumbbell has its mass close to the axis of rotation as you wiggle it, and so it's easy to rotate. But if you take that same mass and move it further away from the axis, it's harder to rotate, so it has a greater rotational inertia. And this is actually used by tightrope walkers. He will carry a long pole that has a high rotational inertia, and that keeps him stable. So it's important to know that for any particular object, to specify the rotational inertia, you must specify the rotation axis. So for example, you've got a pencil. If the rotation axis is the long axis of the pencil, then the rotational inertia is very small. It's easy to spin a pencil around its axis. However, if you change the rotation axis to be perpendicular to the center of the pencil, then it's got a greater rotational inertia. It's harder to rotate around a vertical axis. And if you move that axis to the side, again rotate it around this vertical axis, it's even harder still, so the rotational inertia is greater. Torque. Torque is the tendency of a force to cause rotation. And here we have a torque wrench pictured, which measures the torque on a bolt or a spark plug in foot-pounds. So torque depends on actually 3 factors: the magnitude of the force, which I guess you can measure in pounds, the direction in which the force acts, and the point at which it is applied on the object, which gives the lever arm measured in feet here. So there's an equation: lever arm times force. The lever arm depends both on where the force is applied and what direction it acts. Simplest thing is a perpendicular force just gives a lever arm, which is the distance from the rotation axis to where the force is applied. So as you move this mass out, the torque of the mass on the ruler, with the rotation axis being this hand, gets greater and greater. If you have a wrench being pulled at an angle, then the lever arm is the distance between the rotation axis and a line that's drawn through the force. And that lever arm makes a 90-degree angle between the line that goes through the force and the line that goes through the rotation axis of the object. And so here the lever arm is less than the length of this wrench because you're pulling it at an angle. If you pull it right at 90 degrees, then the lever arm equals the length of the wrench. And it can be less than, but it can't be greater than. The only way to increase the lever arm is to actually put an extension on the wrench, and here you've got a lever arm greater than the length of the handle. Center of mass is the average position of all the mass that makes up an object, and the center of gravity is the average position of all the weight in an object. And since weight and mass are proportional here on Earth, the center of gravity and the center of mass are the same thing for pretty much everything here on Earth. And you can see that the center of gravity of this baseball bat as you throw it follows the same nice path as a ball would go as you throw it, as the rest of the bat rotates around its center of gravity. Stability means that the center of gravity is over the base of the object. So if we draw a line straight down from the center of gravity of an object, and it lies within the parts of that object that are touching the ground, then it won't tip over. If that center of gravity falls outside this base, as we call it, that's when the object tips. Centripetal force. A centripetal force is just a force which pulls an object towards the center. It's a center-seeking force. So for example, if you're whirling this tin can around in a circle, this tension in the string pulls towards the center and provides centripetal force. Centripetal force depends on the mass of the object, the speed that the object's going, and the radius of the circle by mass times v squared over r. Example, here you've got a car going around a curve. The centripetal force is what keeps it on the road. If the road is wet or slippery, the centripetal force is less, and so it is not enough to keep the car on the road, and the car will slide off into the ditch. So the centripetal force is center directed. If you're an occupant in a rotating system, you will seem to experience an outward force, and that's called the centrifugal force, meaning center fleeing. So a centrifuge tends to take sediments and pull them towards the outside of a circle, and that's the centrifugal force. So one common misconception is that a centrifugal force would pull an object towards the outside if the string broke, but that's not true. What happens is if a string breaks for an object going around in a circle, then it would fly off tangentially, according to Newton's first law. So whatever velocity it most recently had, it will continue with that velocity in a straight line. Okay, so when you're in a rotating reference frame, then the centrifugal force is a force in its own right. You really do feel it. So for an example, if there is a tin can going around in a circle and you're a bug inside that tin can, you will really feel this force pulling you towards the bottom of the can. And maybe even the can could be filled with water, and the water would stay in the can for the same reason. Angular momentum is analogous to linear momentum. Okay? It's an inertial, it's an inertia of motion. And we had linear momentum was mass times velocity. Well, angular momentum is rotational inertia, that I, times the angular velocity. It's an analogous equation. So for an object that is small compared to the radial distance to its axis, like a little point particle going in a circle, the angular momentum is the mass times the tangential speed times the radius. Okay. So a whirling ball at the end of a long string will have mvr, or a planet going around the string. That's how you compute its angular momentum. And an external net torque is required to change the angular momentum of an object. That's the rotational version of Newton's first law. An object will maintain its angular momentum unless acted upon by an outside torque. Like here's Paul Hewitt. He's providing a torque to this wheel, and that's causing it to change its angular momentum. So the law of conservation of angular momentum says that if there's no net torque, then the angular momentum stays constant. Okay, and that's analogous to if there's no net external force on a system, the linear momentum stays constant. So here's an example of someone who is spinning with some angular momentum and has a high rotational inertia I and a small angular speed omega. Okay. If he then pulls the masses inwards and reduces his rotational inertia, if the angular momentum doesn't change, that means he has to increase his rotational speed to keep the conservation of angular momentum. And that's why he spins faster and faster.